Welcome to this video, in which we will explore a case study on the electrification of industrial energy supply by producing and importing hydrogen. The case study is on the Port of Rotterdam, and that's rapidly transforming into Europe's leading hydrogen hub. And this development is driven by the urgent need for decarbonization and industrial energy supply. Central to this transformation is the integration of offshore wind energy into the capacity of the electricity grid. So offshore wind energy plays a pivotal role in the Port of Rotterdam's hydrogen strategy. By 2030, the port aims to connect 7.4 gigawatts of offshore wind capacity to its energy system. And this electricity can be used directly for industrial energy supply, and it can be used for production of hydrogen that can act as an energy carrier and can support the making of higher temperatures that industry needs. In order to produce hydrogen, the offshore wind capacity feed large-scale electrolyzers, converting water into green hydrogen through electrolysis. The first 200 megawatts electrolyzer is already under construction, with a target of 2.5 gigawatts of electrolyzer capacity by 2030, which is more than 10 times the current capacity. The materials used in offshore wind farms are critical to their efficiency and also durability. Turbine blades are typically made from composite materials, such as fiberglass, reinforced epoxy, or polyester resins, chosen for their strength to weight ratio and resistance to harsh marine environments. The towers and foundations of the windmills use high-grade steel, often coated with anti-corrosion layers to withstand saltwater exposure. Offshore wind production also means the installation of cables and stations that transport the electricity from the sea to the land. Electrolyzers are the heart of hydrogen production. In Rotterdam, polymer electrolyte membranes, PEM electrolyzers, and alkaline electrolyzers are being deployed. These systems require materials that can endure high voltages, corrosive environments, and thermal stresses. Titanium, nickel, stainless steel are commonly used for electrodes and cell frames due to their conductivity and corrosion resistance. Given the scale of hydrogen production envisioned in Rotterdam, modular designs are mostly chosen, allowing for phased expansion as offshore wind capacity will grow. To distribute hydrogen across the port and beyond, Rotterdam is building an open access hydrogen pipeline network, part of the international HyNet work and Delta Rhine corridor. And these pipelines must handle high pressure hydrogen safely and efficiently. Materials like high strength carbon steel with internal coatings are used, and in addition to pipelines, Rotterdam is preparing for hydrogen transport via barges and other ships. And this requires specialized storage tanks made from stainless steel or composite materials, capable of maintaining hydrogen at cryogenic temperatures or under high pressure. Terminals are being adapted to handle hydrogen carriers such as ammonia, methanol, or liquid organic hydrogen carriers, LOHCs, each requiring tailored materials and safety systems. In conclusion of this case study, the Port of Rotterdam is spearheading industrial decarbonization by integrating 7.4 gigawatts of offshore wind energy into its grid by 2030, powering large-scale electrolyzers to produce green hydrogen, and the case highlights the critical role of advanced materials like composites, titanium, and high-strength steel in building durable wind turbines, electrolyzers, and hydrogen transport systems, including pipelines and maritime infrastructure. And this all means that recyclability, life cycle emissions, supply chain transparency must become key criteria. The hydrogen infrastructure is a complex, multi-material system that bridges offshore wind energy with industrial decarbonization. And from the composite blades of wind turbines to the high-strength steel of hydrogen pipelines, each material plays a vital role in ensuring safety, efficiency, and circularity. For all elements of technology, circularity plans have to be made and are made already. We can summarize this as the circular energy transition that does not only focus on the reduction of carbon emissions and climate goals, but also on the recovery of critical materials from energy technologies and energy materials.